Hey guys, Mr. Betts here. Before you watch this video, I would like you to try to do this page on your own. So this is the second page in the packet for rates of change. And so I want you to try it on your own before I go over it with you. So if you haven't done that, pause the video, finish this page, and then play it and follow along. So hopefully at this point you have at least attempted this. The idea here is we want to determine whether the phrasing of something is going to indicate an instantaneous rate of change or a derivative versus an average rate of change, which is going to be a slope of a secant line. So we're looking for clues as to whether something's going to be happening at a particular moment versus happening over some time interval. Okay, so at a particular moment, instantaneous rate of change, over a time interval, average rate of change. So number one, over the time interval from t equals 2 to t equals 5, this is over some extended time interval, a 3-second time interval or a 3-minute time interval, depending on what units are. So this is going to be an average rate of change. After 3 seconds have elapsed, that is a particular moment in time. So it's not saying during the first 3 seconds, but it's saying at the moment after 3 seconds have elapsed. And it's not indicating over all of the time after 3 seconds. It's just at that moment after 3 seconds have elapsed, that's going to be an instantaneous rate of change because it's at a particular moment. Same thing with number 3, at noon is a particular moment, so that's going to be an instantaneous rate of change. Number 4, during the first 5 minutes, this is going to be a time interval. Not a particular time, but over a 5-minute period. So this is going to be an average rate of change. Over the 12-hour time period, same thing. This is an extended time period, so this is going to be an average rate of change also. And then if we say when t equals 7 hours, so when t is some particular number, that's going to be an instantaneous rate of change. In the second part, we want to look at units and think about what the units are going to be on a rate of change. So it says units for derivative here, but really these are going to be units for a derivative or an instantaneous rate of change, but they're also going to be units that we would use for an average rate of change. Either way, we're going to be dividing the units. All right, we want to keep in mind what dependent and independent mean. So remember, dependent means that it depends on something. So that's going to be the value of the function. That's going to be like the y-axis or the vertical axis. Independent is the horizontal axis. So time is independent typically because time just moves on. So time is usually the variable that we plug into a function, and that's usually going to be plotted along the horizontal axis. It doesn't have to be plotted along the horizontal axis, especially if we're talking about like the elapsed time for some particular event to happen, and then that's graphed based on some other variable. So when we're taking a derivative, remember we're finding slopes, and slopes are a vertical change over a horizontal change. So when we are looking at units, we're going to be looking at vertical units divided by horizontal units, or in the words that we're using here, dependent units divided by independent units. So once we know that, this is a very easy exercise to complete. So in the first one, it's already been done for us. Dependent is dollars, independent is hours. So units on a rate of change are going to be dollars per hour. In the second one, we might have an area function here. So area is measured in square centimeters. T is measured in seconds. So the area of something is changing with respect to time. So the units are going to be square centimeters per second. In the third one, W is measured in kilograms. Maybe W is representing a weight, although we should know that kilograms would be indicating a mass, not a weight, where weight takes into account the masses of the objects and gravity. But talking about some sort of weight or mass relative to the volume of something. So it looks like we're looking at densities here. When we take a derivative, again, it's going to be dependent divided by independent. So we're going to be looking at kilograms per cubic meter. The third one looks like M is measuring miles per gallon, so that might be the efficiency of a vehicle. So how many miles a car can go per gallon of gas. V is measured in miles per hour. This one we're actually going to have to do a little bit of math. So I'm going to do this off to the side here. We're going to have miles per gallon. I'm going to write it as a fraction like this. If we write per miles per hour, as you might guess, we might be able to do some canceling if we write this as a division problem. So if we have miles per gallon divided by miles per hour, and then we multiply by the reciprocal. So I'm going to back up again here. So instead of dividing by miles per hour, I'm going to multiply by hours per mile. Miles are going to cancel, and the units we're going to get on our answer then are going to be hours per gallon. So it may not be immediately obvious what this means, but it does have a pretty useful meaning. Basically, what this is saying is if we know the efficiency, the fuel efficiency of a car, and we know how fast the car is going, then we can figure out how many hours we can drive per gallon of gas. So a derivative in this case is going to essentially give us an efficiency of how long time period a gallon of gas is going to last us.